Machine learning is an interesting area because not only do you need to code to do it, but you also need various areas of math. And one of those areas is linear algebra. So in this video, I want to give you the very basics of linear algebra that you will need for understanding machine learning. Linear algebra is really crucial for understanding how machine learning algorithms work. It's not just enough to apply them, you also want to understand what goes on behind the scenes so you can catch errors and optimize what you're doing. For example, in deep learning, we have a neural network that might look something like this. On the left side, you put in your input data and then it goes through the various stages until it comes out at the end. But really, if you look at what happens behind the scenes, it kind of looks more like this in each stage. You put in the data in an array form or as a table of data, and then at each layer it gets transformed. You multiply a matrix, which are the weights, with your data, and out comes another form of your data, and so on. And all of these steps and transformations are linear algebra applied to your data. And it's not just deep learning. Many other machine learning algorithms also use some form or some parts of linear algebra to get to their solution. Okay, so now that we've got this out of the way, let's look at the first simple object of linear algebra, and that's a scalar. A scalar is basically just a single number that's just math talk for single number, and you use a lowercase letter to describe a scalar. So for example, if you choose like a real number like 3.2, then you would write in math something like, let x be from the real numbers, like I've written here. Then the next thing are vectors. A vector is basically just an array of numbers or a list of numbers. And you write it as x out of r to the power n, for example, if it's a vector of length n. And then if you want to show the content of it, then oftentimes it's written as a column vector, and then the elements inside of it are x1, x2, x3, and so on. An important difference to coding notation is that you don't use square brackets to access the different elements. Instead, you use a subscript, so you write a little one a little bit lower than the x. And importantly, and kind of annoyingly to code math applications, is that in math, the first element is x1, whereas in programming, the first element of an array usually is x and then square brackets 0. So you start counting at 0 in coding, and you start counting at 1 in math usually. Depending on the context, you might imagine a vector as a point in space, or also an arrow to a point in space, like in this image here. Now, vectors were one-dimensional, so they only have one dimension of entries. But then the next step here are matrices. Matrices are two-dimensional arrays, or you could also look at them as a table of data. To write about a matrix in math notation, you use uppercase letters like an A, and you use r to the power of n times m for n rows and m columns. And here's an example for a matrix with 2 rows and 3 columns. To index the elements, you again use subscript, but you index first the rows and then the columns. But what if you have more than 2 dimensions? Well, that's where tensors come in. So tensors are basically just the same thing as a matrix, but with 3 or more dimensions. You use the same notation with an uppercase letter, and then in the exponent you say the different dimensions and like how large each dimension is. So n rows, m columns, and then l stacks, or however else you want to imagine the third dimension. Tensors are not really a math thing, but they are very common in machine learning, especially deep learning. In deep learning libraries like PyTorch or TensorFlow, as the name already implies, most of the data that you save will be in the form of a tensor object. And a very great example is a stack of images. So an image is two-dimensional in nature, so you have like a height and a width, and then there are pixels inside of it, so that's 2 dimensions. And then the third dimension of a tensor of data would be that it's multiple images at the same time. So you can imagine it as a stack of papers. If you would print them out and stack them on top of each other, they would form a cube, right? So like it's a 2-dimensional image, and then you have multiple of them, so that's the third dimension. And you use stacks of images or like groups of data in general to pass them through a neural network at once to use parallel computing. But really the key takeaway here for linear algebra are matrices, because basically tensors are just matrices with an extra dimension, vectors are just one-dimensional matrices, and even scalars, the single number, you can think about them as a one-by-one matrix. So let's look at some important operations on matrices. One of those key operations is the transpose, or transposing a matrix. Transposing a matrix means mirroring it along its main diagonal. Here on the side is an example where you can see that the main diagonal stays the same, the 1 and the 4, and then the 2 and 3 change their spots because you fix the diagonal and then everything on the sides gets flipped around. You can also apply this operation to a vector. So if you have a column vector, and you can also apply the transpose to a vector. If you start out with a column vector and you then flip it along the diagonal, it doesn't really have a diagonal, so you only fix the top entry and then you flip it from downwards to the side, and then you have a row vector. The next key operation is addition. And addition of matrices only works in theory if they have the same shape. So if it's a 2 by 2 and a 2 by 2, you can add them up entry-wise. So you take the top left of each and add those numbers together, and then you take the lower left and add those two together, and so on. Of course, there's also matrix multiplication, but the process of that is a bit more difficult, so I'll save that for another video. But what we can talk about is scalar multiplication, and that's where the scalar from the start of this video comes in. Scalar multiplication means you take a number and multiply it with a matrix. And in that case, you multiply the scalar with each of the entries in the matrix separately. And then the end result will be another matrix of the same shape as the original matrix. Now, when talking about addition, I just mentioned that the two matrices have to have the same shape or the same dimensions. But in many programming languages like Python, there is some simplified notation that they implemented, so you can add matrices together even if they have different shapes. The idea here is to add a smaller matrix or even a vector to a larger one by taking the smaller one and duplicating it next to each other, and then creating a matrix that has the same component over and over again until it matches the bigger one. Now, that might sound a little weird at first, so let's look at an example. One way to do this is you could add a scalar to a matrix, and in that case, the scalar, the one number, if you add it to a 2 by 2 matrix, it will be copied until it will be added to each entry of the matrix separately. Now I've written the end result here, but you can imagine that in a step in between, the 2 will be extended to a 2 by 2 matrix that is just full of 2's, and then the two matrices can be added normally. A very common application of this in programming is if you add a vector to a matrix, and both of these have the same number of rows, but of course the vector only has one column. So if you then add it to a matrix, for example to a 2 by 2 matrix, then the vector will be copied once and added right next to its original vector entry, and then it forms a matrix, a 2 by 2 matrix, where the vector appears twice. And then they are again the same shape, and you can add them together like usual, like it was intended in mathematics. This broadcasting, as it's called, is an incredibly efficient feature, and it's like very useful if you know what it does, but you have to be careful if you don't intend to use it and you just made a mistake in your dimensions. The programming language won't tell you that those two matrices don't strictly have the same shape, so you can't really add them. It will just do this broadcasting thing behind the scenes and will not warn you. So you need to be extremely careful when dealing with different sizes of matrices and checking that they have the shape that you intended for them to have. So that's it for the main objects of linear algebra that you will need for machine learning. Thank you so much for watching this brief introduction, and I hope to see you in the next video. Bye!